Hello, allow me to continue and then go back a little bit of recapitulation on this thing. So, if you look at my presentation, sir, can I see the PPT? Yeah. If you look at my presentation, you will see there that I had started it earlier saying all product design is a beehive of activity and it is not a pigeonholing. Seeing two things, pigeonholing is separately people deal with things and then the pigeons do not intercommunicate, the purpose is okay, no problem. In this case two things are there. One of the first thing is that they have a common purpose. I do not know what it is other than I do not steal honey, I make others steal for me, but then I do not take honey, so it makes it even. One is making food for its survival and building this beautiful what do you call a beehive. In case there is some threat, we have a stinger which is poised for attack. So, if you are not a threat, of course, there is no problem, it is good. Same thing happens with electronic product design. So, we have here so many of these things, the core of it is probably the small bit of actual product. So, going a little closer, we will notice that something which is equally important is probably all this stuff, saying there are standards and there is product management, meaning the how do you introduce the product. People are not ready to buy your most advanced product as you like. So, I have here a shameless copy, a clone. Sorry for the words, you see here the moment you look at it, you do not need to whether I add this pointless color bar or not, you know very well it does not make any sense at all, but then the original costs probably 70,000 rupees, it is a lot of money. This costs 7,000 rupees, 1/10 of it. So, I can keep losing them and tracking them, but then you say that there is something to it which wants people to copy. So, I will stop, I will now get back to my presentation. So, the product management are the people who decide what is it that we want. Initially nobody would want a fully what do you call all the bells and whistles product, because the market is not ready and then we do not even know whether somebody will buy it. So, I am sure manufacturers are working about it all the time. People say planned obsolescence, the issue is not about planned obsolescence, the issue is how to introduce products to the market. Unless people try a basic product, it is unlikely that they would want to go to the fully loaded product. Very much related to this is something called industrial design. When people talk about industrial design, what they mean is, long ago once upon a time it was about products which are made in the industry. Right now definition is saying making technology humanizable. And two things, traditional product designers especially like me, we are caught up in how to make a better product and the technology of it. But the user would not want that much of technology, there is RAMs, ROMs and MB, MP and I do not know, we are all strong with pixel, but we really do not know what is a voxel. So, we are not yet ready for it. Industrial design takes the user's point of view. They say the whole issue is about experience design. So, I will stop here, I suggest you go to the other things saying check up about it. And then something which is very much related to it is the new manufacturability. So, I have shown you a clone phone which the fact that they are able to sell at 7 or 8,000 rupees shows that probably it is made at half the cost. So, I expect the whole thing is probably assembled and it leaves the OEM premises for much less, maybe around $50, and then you pay what do you call $1,000 for it is not my problem, but the issue is manufacturability has ensured two things, that things are made within a target cost. You have a target cost and made in sufficiently large volumes, and once the design is ready, it can be made by anybody anywhere. So, little hard to take, but the reality is like that is what is manufacturability about, saying you should be able to make it anywhere in the world and then sell it wherever you like and all that. Related to this, I will just go back here, three things are very much related to this, I will come back later. Now, when we come to the actual core product, we will notice that the interconnection technology, thermal, environmental seem to make a lot of difference. So, latest is that this related to manufacturability is computer-aided manufacturing, saying once you create certain files, followed once you create a certain file, that same file should be able to be used by the manufacturing people there. Then, if you remember, I had talked about CAD techniques. Advanced is CFD and all sorts of numerical and what you call finite element analysis, and you see here, oh, I am trying to look in the monitor and do. We have now automatic test equipment. In fact, things are so standardized that PCBs are not checked in this thing, the components are real and they are all checked. Components are shot at a PCB. So, you have a component shooter which at a mad at least for an old fellow like me who is suffering from various time frame problems, they are just shot at the PCB and miraculously they seem to stick to the PCB and something happens, something else. In the end, an automatic test equipment just make sure that it works, and I understand they talk about a yield, saying all the PCBs work all the time and not just then later on also. In case something fails, we have maintainability. You see there we have that maintainability, how well things can be maintained both by authorized service people, or coming back to my clone phone, something beautiful has happened. You do not even need to go anywhere, all the time updates are available. Even should you buy the original Apple, it gets updated automatically. It needs your permission only as a formality, and then otherwise no. I do not know if it is real or not. There is a kill switch also. If they want, they can shut off the phone, but they will never do it. That is, I understand the kill switch or jailbreak and all that are not part of this. So, we have these issues of CAD techniques. Okay. If you start properly, you have several things, and then you have computer-aided manufacturing, automatic test equipment and maintainability. And the moment you start with CAD techniques, you just go up here, we come to new type of controlling heat. So, it is all covered here, saying in maintainability, assembly, installation, mean time to repair and long term use, industrial design, user satisfaction, ergonomics, aesthetics, fitness and feature integration. So, when somebody buys a designer something, including a designer watch, I have a funny looking designer watch. I am surprised because it does not cost too much. It is a Fitbit, it is one of the trackers, it is costly. In India, it is very costly. The original, I do not know how much it is, like so many of the things you see with me are all presented. It costs 15,000 rupees, but I am very much thrilled that it comes with a metal strap and even the other straps what I have, and then if you see the metal strap also it has a magnet, and then I am very much thrilled. What I want is visible, what I do not want miraculously goes away. That is what is about this integration of features. And again coming back to product management, in the beginning we have no choice but to have what is called an entry level. Not long ago, maybe 50 years back, we just had a car, you lived with it forever. Well, I won't say the future is a shock anymore, the future is here. Right now people talk about an entry level car, saying first time buyer entry level and all that they talk about. Eventually they, depending on where they use it, if they are using it off road or anything, they will go into sports vehicles, and depending on their thing, you have commuter segment and so on. So design tries to make a trade off between various things. So you have something which is at an entry level. In India, when we started, cars were having, I do not know, one stick on the side. Some of the time the stick was stuck to the steering wheel, and then they had lot of pedals at the bottom, push it here, there and all that. We have got used to those things. Now these days I think it is unlikely anybody buys a car which does not have power steering, assisted brakes, power windows, climatizer, SRS airbags, then what do you call dash cam, then you have parking sensors, you have front everything, and at least what we do not need or I have never been able to use is the cruise control and GPS trackers and so on. No? This is how features are. Now if somebody asks me, I crawl at the thing, I live in a place called Bangalore, where on good days in bad traffic we cover 10 kilometers an hour. So do not ask me what happens on bad days and what it is, and then yes, if you have been able to make it faster, drive fast. I can't, I live in. So the thing is what the size of the engine should be, that is how things called hybrids, micro hybrids, and how you store energy, all this design takes care of these things. In manufacturability you come about fabrication, the quality, costs and finishing. Something should look good. Even things like a phone, you do not look at all the features and order it online, it is unlikely. Even if you are to order online, the positioning in your mind is very, very critical. Part of it is this finishing, how well parts fit together. Something which looks good, it gives you a measure of quality directly. Something again related to the various types of costs involved in making it. Things have been evolving, and the other extreme come here saying maintainability. After installation, how do you install things? Then if you remember, I was talking about hot plug-in. So happens with power supplies, happens with fans, happens with actually boards. If you want reliability, you end up with that. And then after a failure, how quickly can you repair something? The plumber needs to be on your premises before you get flooded out. Not a big flood like a cyclone, a normal drip, eventually very irritating. We have the feeling that drips are made to make sure that not the drips here, but the, I think people call it a tap or a faucet dripping. In fact, Disney made a movie out of it. And long term use, backwards compatible. So if somebody has what you call a old rotary dial phone, the new devices must have the way of converting it into pulse dialing phones. Okay. So I have an option between pulse dial and DTMF and the new technologies, and then something related to his assembly and disassembly. So I will not talk too much about it. Next slide. talks about the environmental, the interconnection and the thermal aspects, okay, which have come nothing from the actually from the decent thing. See here we have thermal environmental interconnection, little closer, this is the box we are talking about. This thermal very peculiarly comes to what looks like a intuitively contrary thing, saying if you seal something you can't cool it. If you want to cool it, you have to make sure you make holes, no, you have a dotted line. Later on I will come to these things. This is what early on I had shown you, saying we have conductivity from here. You see here the heat is being lost just outside from the PCB itself, and then something from the leads, and then this blue color, and then you see here something from the case. If you are to have a case which is reasonably conductive and then it has very good convection, and maybe you can, is there a way of doing it, maybe we can do better. Exotic cooling techniques include phase change, same thing what looks very see the previous slide shows as a idealized thing. This is a heat pipe. A practical heat pipe is a little more, but I am not much of a fan for it. Now you see whenever we talk about things like that, all the time they can't be in a benign atmosphere. So you have this is a weather station and something, and then this one is I think you know what it is, no? Right side is a what do you call, we have a hybrid rain what do you call device, and these are all things in which I have worked. So we have an antenna here, I mean actually this is a reflector, that is an antenna, we have various devices, all these things we end up with what was actually, if you see this it looks like a what you can find inside a lab, and then but you end up with using it outdoors. So you have a temperature compensated pressure sensor here. Some of these things need to be maintained at a constant temperature. You understand, the sensor itself is expected to be maintained at a constant temperature. So one of the common things, while the earlier picture showed you something about heat pipe, this is directly taken from the catalog of this Meerstetter engineering. So since it is retrieved recently, I suggest look for it, you understand, no, Meerstetter engineering. Why is it is because it is only, well I have no interest, I mean I am sorry, I have no pecuniary interest in the whole thing. I am very much interested that people understand, and instead of you are searching this thing, I have read through, I would like to tell you about it. First of all, TEC controllers and Peltier elements. So TEC, subsequently it is explained, you should see what it is. So the contents are all estimated here. Thermo-electric cooling, understand, no? Thermo-electric cooling can be used for various applications, even when active cooling below ambient temperature or high temperature precision in combination and so on is actively regulates the temperature of a given object or a case. You see, this is where the criticality comes. If you must ensure that precision of the order of fraction of a degree has to be maintained, it is very much possible for us to maintain it. If I showed you that pressure sensor which the earlier picture showed you, obviously it does not need it, but imagine crystals for transmitters. They have given, I mean very narrow what do you call frequency band, you cannot afford to make it drift at all. So, the main crystal is maintained in a oven, and typical temperatures are around 70 degrees. I think most proportional control oven crystals work at around 70 degrees, but imagine inside the enclosure if the ambient goes above that. So, we have the thermoelectric controllers, thermoelectric cooling in combination with the Peltier element is actively regulating the temperature of a given object or case, done without acoustic and electrical noise, vibrations and mechanical moving parts. All other thing you have seen, including the heat pipe, it ends up with vibrations and acoustic noise. It may not be directly observable, but that bubbling is not a very comfortable thing. If you know that something is bubbling inside, you know what it is. So, it is not a your what you call tummy growling, but some mild noises. Changing from cooling to heating is possible by changing direction of current without making any mechanical changes. So, you must have heard of the air conditioners which are reversible and can be used as heat pumps. I will say more in what you call they work occasionally. We do have a problem. We want a room inside to be heated when the temperature outside is very cold. Something which is outside the thing, the outdoor unit has the problem of trying to exchange, I will say cold, trying to pull in heat from outside and passing it to inside. Because outside, imagine if it is already condensing and the temperatures are really low, not much can be done. Differential and the absolute temperatures are limited. But in the case of Peltier, it looks like it is not so much of a problem. Of course, alone very rarely they are used, they are always used in conjunction with other things. There are temperature limits when operating Peltier elements. Elements are available with a maximum temperature of 20 degree, where this limit is divided by the reflow temperature of solder and sealing. Limit where the temperature will rise again and more current is supplied. This is because of the power dissipation within the element drawing more current than I max. So, we have all this stuff heating and cooling, and how much of what you call cooling can actually be done, because there is a heating inside the whole this thing. So, not as if you can just, it is not a linear thing like that, tremendous amount of positive current you put and it keeps cooling down, not true. In this case maybe it is possible only for us to operate around the 0, because it is still in the linear region partially. After you go down a little, we still have a problem. Designing a thermoelectric application, cooling is the critical part. We will take the case of cooling an object and as an example for the design. You see here, I will see if I can enlarge it. It does get enlarged. So, we have temperature sensor, observe what I call the object itself, and then you see here very important thing is thermal isolation. I am sure some of you have checked on the videos on YouTube. They will show you, a small, show me my face, sir. They will show you a small plate which is typically around 30 or 40 mm square, and then you have what you call a power supply pumping in current, and then you put a few drops of water and show you how quickly it freezes. Reality is, while that is okay, it is not a very efficient way of it. Instantaneously, while the thing may work, there will always be a short circuiting from heat from the other side to this. To isolate it, we need to pack it into a proper thermal isolation, which is given here. This thermal isolation is very critical to make sure that there is no short circuiting from both the sides, and the you see this red and what you call black. So, I expect that I will put it as out high and out minus there through colored wires, and you have a plate here, and then we have the monitoring, something which monitors the sink temperature. So, usually you have a thermistor or sometimes something else, some other sensor, and then two critical things what you need to do is to spread the heat. You probably need a copper or aluminum plate to give it certain amount of stability. Then you have the actually the Peltier element, then the whole thing afterwards the different elements will be explained in the following chapters, and very critical is you also have a fan there. So, depending on the criticality of the design, total amount of heat load, because heat load heat loads is critical. Estimating the heat load of the object to be cooled. So, part of it is make sure you minimize the heat load. So, no point in what you call cooling a large volume when the thing which needs to be cooled is a small volume. So, it is a very huge what you call data center place. What is valid for the whole room and whole thing, it is also same valid in a small chip that needs a close control. Define temperature working range, both the working ranges, that is the ambient with which you exchange the heat as well as the device which needs to be maintained. Choose an element that satisfies the requirements, easier said than done. Little bit of last step, test your experiment, set it, prove it, loop until you get into a reasonably satisfactory thing. Choose a TEC controller with enough power. This seems to be also equally critical, and then this, since the manufacturer here tries to deal with the whole situation, he supplies what has been tested already, experimental test up set, experimental setup has been tested. So, in case it requires let us say directly one big connector which connects to the whole system, the Peltier and then the temperature sensor and so on, and maybe something for the fan and then input, and something very critical is to have a backup battery, saying do you have a reasonably sufficient, maybe a 12 volts 20 ampere battery which are likely to find the moment all this stuff is there, and then something to keep the battery running, there will not be any runaway that accepts it. So, there do all this, choose a TEC controller, choose the object temperature sensor and the optional heat sink sensor. You see very coolly he has written optional. So, I expect that it is probably required that you sense. The idea is saying the final ultimate thing is the object temperature, the device under control, and if you know the heat sink sensor, you can proactively design if you think. Choose a heat sink for the Peltier element which once again comes to the heat load and the working range. Choose a fan to air the heat sink, meaning to give convective what they call improve the convective heat transfer coefficient. Again he has given optional, depending on if you want it complicated you have a fan, if you do not have a complicated arrangement, maybe a simpler system by which a natural thing will occur. Choose a power supply, test your experimental setup. An important parameter is the amount of heat to be absorbed from the surface of the TEM or Peltier element. Depending on the application, there are different types of heat loads to be considered: power dissipation, radiation, and then all this, no, and dynamic, the rate at which the total amount of power keeps increasing or decreasing. So, which is likely to be had. Heat load will be transferred from the cold side to the hot side where the heat sink is located. So, an object has to be cooled to some given temperature. If the object to be cooled is in contact with the cold surface of the thermoelectric, the desired temperature of the object can be considered as the temperature of the cold side of the Peltier. Two design parameters when outlining cooling application: object temperature range, sink temperature range. This is all typically a Peltier TEC module maker can guarantee you. From here everything else is yours. So, you need to work out saying the delta T that it can come. Single stage Peltier elements are capable of producing a temperature difference of 72 degrees in case there is no thermal load. If a greater difference is needed, stacked modules have to be used, cascaded. While I am happy, that a nice figure like 72 and all is quoted, I have never seen it in real life, because the load is so much that not easy to maintain such temperatures. So, maybe 20 or 30 degrees is what is more practical. If you want more, you are always cascade it, like I will show 3 P N, again another P, another N, P. So, NP, NP, NP and all that, no, they are all stacked together. There you can just what you call literally attach one to the other, hot side, cold side, which will become the hot side of it, which will become the cold side of it. 2 is very common, cascading 2 is very common, with little bit of again how do you paste them together, and occasionally they are also available directly from the manufacturer. So, he gives you all those things. So, the Peltier element produces a temperature difference between both sides due to the current flow. So, besides mechanical properties, Peltier elements are defined by several important things: total power handled, total voltage maximum that can withstand, then the current, and then also the temperature difference it can give. The more the absorbed thermal load increases, the more the resultant delta T decreases. So, this is what I was talking to you about, no? Qmax is the amount of thermal load at Imax which produces a temperature difference of practically 0. We will come back to it later. The value is defined as the maximum possible temperature difference of the element at Imax when the thermal load is 0 watts, which I think looks nice, more of mathematical or leading to precision. Umax is the DC voltage which delivers the maximum possible delta T across the permanent, what you call across the element. Imax is the maximum direct current which produces the maximum possible delta T. So, you see here heat pumped versus current. So, the what you call maximum QC minus Q maximum, and as the temperature difference goes more and more, very little of this can be used. So, both ends say this is useless for us, because unlikely we will have such an overrated thing. Similarly, it is unlikely we have this grossly underrated things also. Operating Peltier elements not at their limits in current and difference yields a greater slope and therefore more dynamic characteristics of the module. when outlining the system, current of the Peltier element should be 0.3 and 0.7 times I max. You understood, no? So, something I will I will probably prefer at this. Okay, these are all practical limits. You understand, no? Around 0.2 times the what you call maximum power it can handle, and similarly the what you call the current, no, is typically about 0.7 to 0.5, or even this, no, the yellow colors and all that. More likely this red is what you will see in news, just a mean at the point, no, just a median figure. Another important criteria is the coefficient of performance when choosing a Peltier. Definition of the COP is the heat absorbed at the cold side divided by the input power of the Peltier. Because when all the small systems are all attached together, you have a large number of small systems attached together, overall things become very poor. So, for convenience sake, they have result of a maximum is minimum Peltier input power, minimum total heat has to be rejected by the heat sink. Therefore, smaller heat sinks can be used, what allows a more spacing device. It is also important in the heat rejection of the heat sink has to be minimized. On the other hand, on optimizing cost, a design with a lower coefficient of performance has to be chosen. So, have a look at it. Okay. Nicely through all the delta T's, no, they have drawn a figure which is typically seems to be a product of these things. So, once again you see where you would like to have the optimum power. So, once again by in this case the product, whether you take this or this are approximately same. So, probably 1 to this 0.3 may be a reasonable area by which coefficient of performance will be good. Two thermal parameters are necessary to select a Peltier element, maximum cooling and temperature difference. Example, we assume an object to be cooled to 0 degrees. Let us say the sink temperature is 36 degrees centigrade, difference is 36. There is a heat load to be absorbed 10 watts. You see, these are very practical cases. As we have a temperature difference of 36 K, single stage Peltier element is sufficient. Delta T maximum, we calculate delta T by delta T maximum, 36 by 72 is around 0.5. So, you have seen this, no? Typically any of these things in relation to Cp, obtain the optimum value of Qc by Emax at the intersection of the horizontal line of delta T and delta T maximum at 0.5. You have seen that, no, somewhere here. Follow the blue lines and read out the value at the vertical axis. So, optimum up to 40 watts can be done. Obtain the maximum value of Qc max at the right vertical axis that correspond to 0.5. Maximum Qc is 20 watts. A Peltier element with Q max between 20 and 40 has to be chosen. Though we started with only 10 watts that needs to be dissipated, you understand, no? Something much bigger saying 20 to 40 watts has to be chosen. I will go for the higher thing only, because initially if something fails, we are in a problem, later on fixing it is a problem. Once your experiment is succeeded and all that, no, maybe reducing it a little or leaving it where it is, because you see while the cost is high here, the size approximately will be the same. They are not monstrously big or anything, they are not as if they are 4 times as big, they are only slightly bigger. If a Peltier element near to the optimum is chosen, a high COP and therefore maximum efficiency is achieved. Element with near the optimum will yield less cost but less cooling capacity, which is also true. Peltier element will be operated near its limits, which is a serious problem. You have seen that, no? Ending up with the limits is a problem. So, the reason why this 40 watts I would prefer to choose is at the intersection and so on, and the value, plot a vertical line, record the value at the intersection of the vertical line and the bottom axis. The optimum is 0.5, using the value I max of the Peltier element, we can calculate the result current. Besides the thermal properties of the the mechanical are also important. So, having decided these, I suggest you go over this, you take the 40 watts thing and so on. So, we end up with a good starting value for these things, and as I said, depending on your own available expertise at your area, you can always make your own electronics or try to see whether you can integrate the same this control and all on your printed wiring board which you already have. If you have a wiring board probably and you already have a supply, somewhere you are getting a rail which is giving you a 12 volts rail, and getting let us say around 80 or 100 watts is not impossible for you. So, you can do something to include all these things here, because very rarely you may be giving the 12 volts into 3 or 4 amps may or may not be required. Actually around the operating point it will be just hunting around a small value, probably around half of it. So, if you can integrate it onto your main design, as a designer you have the choice of calling the shots. Now, we come to what is the size for my application? Do I need a special form of the peltier? What mounting options do I have? The choice of the heat sink for the peltier. So, we have this issue saying how do you, what are all the peltiers that are available, and as I told you very roughly, I told you that we have a 40 mm by 40 mm and so on. So, as you go down here, this various controllers and are all listed here. So, I suggest you go through this a little more in detail and make sure that the things like who are all the fans, so what are the fans you do, what are the power supply requirements you do, and then test setup. So, we have here basic what do you call things about, these are basically things relating to the controllers only, you understand, no, because we are talking about the electronics control about it, the elements, the form factor and all that. No, right now I have no access to the internet as such, it will only, even if I click here nothing will happen, it will just what do you call okay. Kindly you must go back to the what do you call other manufacturers, look for the what do you call peltier controllers and so on. I will try to close this here at this point. And go back to the old what do you call the master book about stuff about how to deal with I am sorry, we do not have it here, elsewhere I will try to conduct it. So, probably I will what do you call stop here at this point and see, start with that sample we have and see what we can do here. So, thank you for this session.